Hello everyone, and in this video, we're going to be talking about the USAJMO problem number 3, which is one of the hardest problems on the test for day 1. So anyway, here it is. Suppose you have triangle ABC and a point D on the circumcircle such that BD is perpendicular to AC. And then you have points E and F, which are the reflections of D across AB and BC. So these are the reflections. And this intersects line BD at point P. And now we draw the circumcircles of EPD and FPD, and they intersect the circumcircle again at Q and R here. And our goal is to prove that EQ is equal to FR. That's what we want to prove. So how can we go ahead and get started on this problem? We want to say something about these circumcircles because they definitely look ugly. And if we take a closer look, you might notice that A appears to be the circumcenter of the circle. So we list that as a conjecture. Because that would be really useful as we entirely get rid of the circumcircle and we just reduce it to AD equals AQ. So how can we go about proving this? We already know that AD equals AE because D and E are reflections across a line AB and A lies on line AB, which means that it's equidistant. So all that remains to do is show that one of these two lengths is equal to AP. Why not just choose AD because it relates to the circumcircle more? So this is equivalent to proving that AD is equal to AP. But now this is kind of tricky to prove. How could we get started on proving this now? If this point here is the foot of the altitude, let's call it X, suppose, then we know that AP equals AD is equivalent to proving that DX equals XP. So it's equivalent to proving DX equals XP. But then if Y and Z are the feet of the altitudes, Y and Z, then recall my video on Simpson lines. If you haven't watched that already, go ahead and watch that, which states that X, Y, and Z are collinear. They all lie on the same line. So let me go ahead and draw that in. And additionally, we know that DE is equal to 2dy and DP equals 2dx if it were, and DF is equal to 2dz. So by a homothency centered at D of scale 2, we have that D maps line YZ to EF. And that means that the intersection points are also preserved, which means that it maps point X to point P. Therefore, dP is equal to 2dx, which means that dx equals xp. So now we know that AP equals AD. Let's go ahead and erase all of this. And we, in fact, have that A is the circumcenter of PED. So now we can go ahead and say something more about point P. The instant you see dx equals xp, it should ring a buzzer for you. Because in a previous video that I created about reflecting the orthocenter, go ahead and check it out if you haven't watched it already. If dx equals xp, then P is the orthocenter of triangle ABC. But we know that dx equals xp, so P is the orthocenter of triangle ABC. In particular, we know that if Q is the intersection point here, then AP equals AQ, which is equal to AD, because A is a circumcenter. And given this, we have that AP equals AD means that D is a reflection of P across AC, And AQ equals AP means that Q is a reflection of P across AB. However, the reflection of the orthocenter across AB also lies on the altitude. So we end up discovering the miraculous fact that CQ is perpendicular to AB. And we similarly have that AR is perpendicular to BC. Pretty amazing, huh? Let's see what we can go ahead and do with this. Now we have that CQ is perpendicular to AB and AR is perpendicular to BC. And we wish to prove that EQ is equal to FR. We're giving a lot of information now, and we've essentially gotten rid of the circumcircles, so we can go ahead and remove those. And Q is a point such that CQ is perpendicular to AB, as over here. And similarly for R. And we wish to prove that EQ is equal to FR. One common tactic used for proving that lengths are equal is proving that they're equal to something else. So let's go ahead and draw EQ and FR in. And let's try looking for lengths in this figure that look like they're equal to these two. And after a bit of inspection, it looks like PD is equal to EQ and PD is equal to FR. If we can prove that EQ equals PD, then by symmetry, PD is equal to FR, and that finishes the problem. So let's see what happens if it works this consequence. We already know that EQPD is cyclic, so let's go ahead and draw the circle back in. It could help. So if these two lengths were equal, if they were, then that means that we have an isosceles trapezoid from properties of circles, which means that QP is parallel to ED. So we want to prove that QP is parallel to DE. But given this information, since P is the orthocenter and Q is a reflection off of it, PQ is perpendicular to BA. And from reflections, we know that ED is perpendicular to BA as well. Since they are perpendicular to the same thing, they must be parallel. So this is true, which means that it's an isosceles trapezoid. Similarly, PDFR is an isosceles trapezoid as well. Therefore, EQ is equal to PD is equal to FR. And we're done. So thank you so much for watching this video. I hope you enjoyed, and please subscribe.